Hello kids, today we will be covering Unit 5, which is Materials and Cycles on Earth, and the first topic in this unit is the structure of an atom. Right. For that, I will start off with a little presentation, some animations that I wanted to share with you guys. This is how we know an atom. There's something inside, and the things running outside, what we call as the electrons and the nucleus. So that's not how the atomic structure is supposed to be. It's for the kids, but you people are normal kids. So this is how we're going to understand how your atomic model works, right? Now, this is the two-dimensional model, the one that we usually see. This is the green one, right? You see over here. Let me just get the laser pointer. Do we have the laser? Sorry, I think, yeah. I'm going to take the green one, right? So this is your structure of atom, right? In an animation, you can see how the nucleus inside the particles inside the nucleus, the protons and the neutrons are moving, and outside we have the electrons, circling around in orbits. This is a two-dimensional model. What's a two-dimension? I'll explain in a moment. And now this is a three-dimensional model. Now this is a rough model. This is not how actually the electrons move, but this is the only animated 3D model I could find closest to the atom. So you can see that there's the nucleus inside, and the orbits are moving in spherical format. So the orbits themselves are also moving. That makes it appear like a ball, right? Otherwise, the atom is supposed to be flat, right? If you look at this two-dimensional model, this would feel like the atom is just a flat disk. But this is not a disk. It's more like a ball. It's like a sphere, since the electrons are moving in the orbits as well as the orbits are rotating. Now this is a simulation of how the electronic cloud outside the nucleus is. You see inside there's a bright center, which we call as the nucleus, very energetic, and outside these electrons, when they're moving around, it appears to be like an electron cloud, just like lightning, right? But a very small scale lightning, because we do know that atoms are very small in size. So you see this kind of an electron cloud forming around the nucleus. These electrons, they're moving at very high speed, so they appear to be like lightning strikes, right? So this is the periodic table, in which we do understand there are several atoms like hydrogen, which is a gas. Then we have a helium, which is another gas. As you can see, these are called atomic numbers. So there's one atomic number, there's two atomic number, three, and then 4 I couldn't find the animation, 5, 6, 7 again I couldn't find, 8, 9 and 10, 8 being the oxygen. As you can see, there are 8 electrons, 2 inside and 6 outside, and this is how different sizes of atoms vary, right? And it keeps on growing up to, you get to the bigger ones, like this is titanium, and this is vanadium, and this is antimony, which is like got 85 electrons. So the atom gets bigger and bigger the more you work on it, right? So let's get back into our lesson, right? Our lesson, just a moment. Okay, this is our lesson, what we are supposed to be covering today, right? Let's get into this. Like, what is the structure of atom, right? So far we have understood that atom is not this goo ball, which is having these some particles running around. So I was just discussing that there are dimensions, right? So what are dimensions? So I'll go with a simple idea, right? Let's take an example of a dot, right? So let's say I draw three x's, right? Let me draw the x and the y, please don't mind, uh, and the z-axis, right? So we've got three x's, three dimensions, just like the corner of a room. Like you have got length, you have got width, and then you've got the height, right? So the three dimensions we see. So a point is just a zero dimension, right? At zero dimension there would be anything. So if I elongate just along one axis, let's say along y-axis, I've elongated that dot, it becomes a line, right? Now I will keep drawing these three dimensions for your ease of understanding that this is the first dimension. Now once I move from the first to the second dimension, you can see that line has become this area, right? We call it as a square. And if I add the third dimension, which is the height, the width, and this length across, right? It would have this definitely some, since it's a cube. So from 1 to 2 and 2 to 3 dimensions, we see that objects turn into solid, right? This was flat, right? This was flat, and this is now you can say 3D, right? Three-dimensional, or this is 2D, and this was 1D, right? So an object, you can say that if you compress the one dimension out of the three, you go back into two dimension, you convert a cube into a square, and a square would be translated into a line, and the line eventually, if you remove all the dimensions, would be turned into just this point, 0 point, we call as 0 dimensions, right? So moving on, so our main objective is to understand the structure of an atom, right? So I told you that an atom consists of three fundamental particles. The ones which are outside roaming around, which are negatively charged, we call those as electrons, right? So the electrons are negatively charged, and inside we have this bulk of particles sticking together. We call that as a nucleus. This whole part, this whole thing is called a nucleus, right? And inside the nucleus you will find that there are protons which are positively charged, and there are neutrons which are neutral in nature, right? They don't have a charge, right? So keep in mind that we do know that the electrons represented by E negative, then the protons are represented by P positive, and neutrons are usually represented by a 0, or you cannot even, I mean, even if you don't put anything, it just figures that it's a neutron, right? So that's an electron, right? And this is a proton, and then we have the neutron, right? So these are the three fundamental particles. The electrons move in orbits, right? These circular paths, these circular paths are called orbits, right? There are two of them for this atom. The more the electrons, the more the orbits are there. So these two are orbits in which the electrons rotate, and inside we have this nucleus, right? So remember, these two are present inside the nucleus. They are also called nucleons, right? So there's another name that we use together for these particles. We call as nucleons, right? So these are the particles in atom, right? So atom is made out of three fundamental particles we call as the electron, the proton, and the neutron, and they form up atoms. And every matter, all matter, right? All matter consists of atoms, right? That means all of us, I mean including me, my pen, this display, this screen that I'm using, right? Everything is made out of atoms, right? Now different combination of atoms form different things. For example, we have metals, right? They have different type of atoms. Then we have plastics that have different type of metals. Then we have glass, right? Then we have organic materials like plants and animals, right? So all of these have different forms of atoms joined together, and at times atoms join together to form molecules, right? And those molecules depend upon how they're joining together, right? We do know that this hydrogen, which is the first atom, then this hydrogen, oxygen, make water for us, right? So we call it H2O, which we call as water, right? That means it has two hydrogen atoms and joined together to one oxygen atom. This is what we call as water. Hence H2, that means two of these H particles and one of this atom of oxygen, right, making water, right? And similar way, we have oxygen gas that we breathe, that is O double bond O, that is O2, right? Oxygen that we breathe. So it has oxygen. Oxygen makes two of these bonds, right? Two connections. So with two oxygen together, they can both share two bonds together. So they form oxygen gas. Then we have hydrogen gas, right? And then we have several other chemicals. For example, we have sodium chloride, right? We have sodium from here, and chlorine, supposedly beneath the fluorine there's supposed to be chlorine here, chlorine 17, right? So NaCl is the common salt that we consume, right? It's Na positive and Cl negative. We'll talk about these in year 8, how these are there. But now let's talk about how these atoms were discovered. And it was a very fun experiment that Rutherford, a scientist who did this experiment, right? He found the structure of atom, and this is the infamous gold foil experiment, right? So what was the gold foil experiment? I'll get into it in a moment. First, we need to understand what is a radiation, right? So I'm just going to clear a little space on above, right, from here, to discuss what radiation is, right? We do know that light from sun comes to us, and we call that as radiation, right? Radiation has many ranges, in which we have the visible range, right? We call as white light, right? We see this light, and then there are invisible ranges, what the ones we cannot see, right? For example, we have a UV, right? We have X-rays, the ones we use for scanning our bones. Then we have yeah, you can say IR, infrared, the ones we use in remotes. We cannot see that ray of light, but it still operates our communication devices, right? Our LCDs, or screens, or any kind of remote ACs, right? So these are radiations, right? So radiation is like a form of light that contains energy. So what this Mr. Rutherford did, right? He took a radiation source. We call it as an alpha, right? Alpha source. Now, what's an alpha source? I'll talk about it. Alpha is a particle which has +2 charge, right? It is a combination of, you can say, two protons, right? It's a ball that contains only two protons, right? That means it's got two times the positive charge. So what he did, that he took an radioactive source which was releasing alpha particles, right? Alpha source, we call these as alpha particles, right? They're not atoms, but they're you can say parts of broken atom, right? Released. And he took a gold foil, he squished it so much into a thin foil, right? Very thin foil. So we call it a thin foil, right? He pressed it, he hammered it so much that it was very, very, very thin foil, right? And when he passed these alpha particles onto this gold foil, he saw that majority of these particles were able to go through on this detector. Now this detector was the uh, fluorescent fluorescent material, right? You know this as night glowing or glowing material, right? What we call as afterglow or glowing materials, or you have seen those stickers that you can find which glow at night, right? This is similar material. That's the photoluminescent, and this is the fluorescent material in upon which, if you throw upon some radiation, it is going to glow in color. So we saw that most of the particles were going through this gold foil, right? That was our observation number one, that most of the alpha particles travel through the foil undeflected. So they were going precisely straight, right? Just according to the source, they were for gathered at this point. So we saw color formation at this point. Some of those particles were able to deflect at certain angles, right, on sides, which represented that they were deflected by something, right? They hit something, or they were repelled by something. And few of those came back, right, at a very sharp angle. Occasionally, an alpha particle travels back to the foil, right? This was deflection backward. So, what can we interpret out of this gold foil, right? We do know that this source, these pink particles that we have, these are alpha particles, and they are positively charged, right? Now, we do know from magnetism that same poles repel each other. Let's say if you've got south and north of a magnet, and you bring another north and south, another magnet, you do know that they will repel each other, because same charges cannot be together. They push each other away, right? This is what we call as repulsion, right? Now this is a similar factor since these are charged particles. I've been very clear in class that magnetism is all due to these fancy little particles inside the atom that causes the materials or some metals to be magnetic in nature, right? So it's a similar behavior over here, that since most of these particles went through the gold foil, we can surely say that most of the space inside this metal foil containing the atoms is empty. So the atom is mostly empty, right? Now, what was the other observation? That some of these particles were deflected. This means that there's a center inside the atom which is positively charged, and hence it is able to repel, right? It is able to repel these particles at a certain angle. And occasionally few of these particles were bounced back. That means that nucleus carries most of the mass of the atom, because these alpha particles went in and hit something hard and came back off, right? It bounced back off. That shows that most of the mass of the atom is inside the nucleus. That means if we take the nucleus, then these electrons, right? These electrons, they don't have much of a mass, so majority of the mass belongs to the nucleus, right? So this is what we can see. Now I'm just going to show you a more two-dimensional figure what was really happening, right? So imagine that these are the alpha particles which are coming in. As you can see, these are positively charged. Some of these were deflected at an angle, right? That means there was some repulsion. Most of them passed straight, right? Owing to the fact that most of the space inside the atom is empty, right? And few particles turned back, representing that it hit a positive center, right? So this was Rutherford's experiment, in which he concluded that atom is a sphere in which there's a very small little center we call as a nucleus, right? This is the nucleus, and he said that nucleus is also positively charged. That's why it's able to deflect these particles like this and like this, right? And since atom gold is a very heavy metal, so he saw that most of the particles were able to pass through it, right? Hence most of the space inside the atom is empty, right? So this is empty space. So we can say that 99.9% space between atom, in the atom is empty. That's what he concluded later on, right? And that tiny 0.01% is the nucleus, which is all of the mass of the atom, right? Because electrons are very small particles, they have literally no weight. So if we say that let's say iron is heavy and aluminum is not heavy, we can say that the nucleus of the iron atoms is heavier compared to the nucleus of the aluminum atoms, right? We do know that the aluminum has a mass of 27, right, grams, for each mole, and iron, which is very heavy, we say that it's 56 grams per mole. And what we say that it's 56, that means the center is heavier. Electrons do not contribute to these masses, right? So before that, what we used to believe, right, about the atom was the first theory that was given by J.J. Thomson, right? I ask you guys to mark this on your book for a reading, to go through this J.J. Thomson model, right? For him, the atom was a combination, a soup or puddle model. This is also known as the puddle model, right? Uh, Puddle model. So the puddle model suggests that electrons and protons are all grouped up together in a single sphere we call as an atom. And remember, the term atom came even before. It was given by Aristotle, right? And he gave the term atmos, right? That means indivisible. That means this is divisible, sorry. Yeah. Right? That means if you take a piece of metal and you scrap it into smaller parts up to a point that you get this powder. So at that point, powder was the smallest thing we could have we could get, right? So if you keep breaking a material down into powder, so that indivisible powder, I mean, you cannot break. If you grind powder, you keep on grinding the powder, you keep on hammering it, I doubt you can get any smaller particles, because once it reaches this powder form, I doubt it's going to turn into atoms right away. So that was the term that he used for this powder, that these small granules, right, granules or powder, granules of powder were atoms, right? He thought that these were the atoms. He had no idea that each grain, each tiny little particle was containing million atoms, right? Millions of atoms in each one, right? He had no idea, because later on when we had advanced technology like these experiments, when these experiments were conducted, we came to know that there are sub atomic particles as well, and the atoms are very, very, very small, right? So this is a bit of a history about the atomic model, right? You can go through this according to the markings I've done on the book. Please read the book for these. Now I'm going to move into the next topic, which is purity, right? Now, when we talk about purity, now since we're talking about atoms, we need to know that what purity means. Purity means only one type of atoms, right? So example would be let's say gold, right? So gold will only have gold atoms, right? It would not have hydrogen atoms in it, right? So if it has any other atoms, you do know that there are several categories of gold which are available. This is the purity chart. I'll come to this in a moment. So we do know that gold is found in, it's sold in several compositions, different purities. We've got 24 karat, 22 karat, 21 karat, different compositions of gold owing to different percentages. So let's get into this carat scale, right? What does this carat scale represents is that if we have, let's say, 24 carat, right, gold, we simply take the percentage out of it, right? How to take percentage purity, right? How to get the percentage purity out of this 24 karat gold. So what we do is that whatever the carat you're buying, let's say I'm going to buy 18 karat gold. So what I do is that we do know that 24 karat is the purest gold. It has no other atom in it. So we take this one in question, divided by the purest gold type, and multiply this with 100%, right? And this will give us the value of 75%. That means 18 karat gold is going to contain 75% gold in it, right? Let's say I have now how to calculate the mass, right? Mass of this, right? Let's say I have 100 grams of 18 karat gold, right? How much pure gold is there, right? That's the question. How much actual gold is there? Because we do know that 18 karat will have other elements in it like copper, titanium, brass. Because gold is a very soft metal. We cannot actually. A lot of people when they're buying gold from the market, and the shopkeepers tell you, "Okay, we're giving you 24 karat gold and whatnot." Please do not trust that. Reason being, 24 karat gold is entirely useless for ornamental purposes. You cannot make a bangle or a necklace using this, because 24 karat gold is so soft that once you wear that necklace, it would start bowing, and after a while you will see that while you're wearing that necklace, it would be elongated or D-shaped. Similar way, if you're wearing a bangle, in your arms, I mean talking about the girls, or a ring made out of 24 karat, you find that even with a slight force, that gold would be deformed, it would be D-shaped, and it will lose its design, right? So hence we maximum that is sold in the market is 22 karat, and that is 91.7% pure, right? That means it contains other elements like copper, right? Copper for making it strong, or platinum, right? To give it a different, more shinier color. Then we have titanium to make it stronger. We use palladium as well, right? Some of these metals which do not affect the shiny nature of this gold, the ornamental value of the gold, we add these metals into it to make it stronger, so that we can make these articles like bangles and whatnot, right? So the more the carat is dropped, as you can see, the dramatically percentages is changing, right? From 22 karat to 21 karat, you're losing quite a lot of purity, right? 23 karat is neither sold. So keep in mind, the maximum purity which is sold in the market is 22 karat. If any gold vendor is selling you a gold article, right, other than the pure biscuits, like pure biscuits, right? The ones you can see, or bars, right? Gold bars like these. These are the only ones that contain highest purity, right? Available. These are 24K. Other than that, you cannot find 24K articles to be worn. Now let's get back to our problem, in which we have, you say, 100, grams of 18 karat gold. How much pure gold is there, right? So first I need to calculate the carats. Let's call this 16 carat instead, right? To make it a little bit different, 15 carats, let's go for it, right? So 15 carat. First, I need to find the percentage purity, right? Percentage purity would be that would be the carat that you're buying divided by the maximum possible carat which is possible, which is 24 for gold, multiplied by 100%, right? That would give you 62.5%, right? Gold. Now, how to get the grammage? Now, simply multiply this percentage, right? 62.5% multiplied by 100 grams divided by 100%. Now we need to remove this percentage. So what we're going to get, this percentage will be cancelled off, right? And eventually you're going to get 62.5 grams, right? So in 100 grams of 15 karat gold, how much pure gold is there? That is just 62.5 grams, right? Now let's revise this question a little bit more, right? Let's say if we still have the same carats, I'm going to remove these blue lines, right? And we're going to remove this grammage, right? 100 gram. Instead, now I give you, let's say, 200 grams, right? You've got 200 grams. So instead of 100 over here, now we will be having 200 grams. Let me change the color so that it's better visible, right? So 200 grams. So we will use 200 grams here instead, right? So out of 200 grams, what is going to be this, right? It is going to be 125 grams, right? So if you do this in the calculator, you'll understand that it is turned out to be 125. So out of 200 grams, only 125 grams of 15 karat gold will be pure, right? I'm just going to change the color so that you can have a better understanding, right? This is 15 karat, so you don't confuse that which number is going where, right? And let me just move it here, right? 15. So this is how we calculate mass in any given quality of the gold, right? These are the quality ratings in which we do know that several percentages are there. So whatever the carat they provide you, you just simply divide by 24 multiplied by 100% to get the percentage out, and then multiply that percentage with the given mass, total mass, to get the gram out, right? You can also work it back, so how much gold was there, right? In if you want to do the reverse calculation, but I doubt there's a reverse calculation at your level as of now, right? Now for silver, we have different gauges because silver is a very low cost metal and we do deal in silver because it's a stronger metal, so we do in much more purity. It is given by this 3-digit number, right? As you can see, there are 3 digit numbers over here, like this one, right? So let's say I have percentage purity of silver, right? For silver, we have a different scale. For gold, we have the carat scale, right? And for this, we have the digital scale. We have 3 digits, right? We go for these 3. So how do we do this? Is that we take the percentage purity in a way that whatever the number is there, right? Whatever the number, we simply divide it by 1000, right? This represents thousandth of a part, thousandth, right? Like if there were 1000 parts, out of which 999 parts would be of silver and rest would be any impurity that is there, right? So in this case we will do this, right? 100%, and we're going to get 99.9% pure, right? So let's say if this number was instead, let's say it was 869, right? If the stamp said that this is silver 869, then instead of the 999, we are going to use instead 869, right? And then we're going to change this value, that will calculate this again, that it is going to be 86.9% pure, right? Again, how to calculate the mass, right? Let's say mass of silver in 200 gram, right? You've got a bar which weighs 200 grams, right? Which has a stamp number. I'm not using this one, right? I'm using this 869, which I've calculated. So how much is going to be there? Again, you take this percentage. So we're going to do this in a different way, right? That this is the 86.9% multiplied by what is the total mass given to you, which is 200 grams, right? Divided by 100%. is the same method. Once you get the percentage purity, you can repeat this step, right? Just like the one we did for the gold is the same, except the purity calculation, the percentage purity calculation for gold and silver are different. For gold, we use a carat scale, and for silver, we use the three-digit stamping scale, right? So this it is going to be. Let me just pull out my calculator, right? So we can easily calculate this by multiplying these numbers. So it's 86.9 multiplied by 200, right, and divided by 100. So that is going to be 173.8 grams, right? So out of 200 grams, 173.8 grams are of pure silver, right? Pure silver uh, atoms, right? Since we're talking about purity, so pure, I told you that pure materials only consist of one type of atoms, right? So this is how we calculate the percentages, right? Now there are several tests that I've brought in. These are not, this information is not in your book. You can check different types of material. At times these shopkeepers, they sell, sell you silver, but that's actually steel inside and coated with some silver on it, right? So how to identify is there first you need to see the stamps inside. Even for gold articles, you will see that it has 22K written on it or 21K written on it, right? You would find that an article you buy for 24K, inside the stamp would be 22K, and once you go back for selling, they tell you that it was 24K that you bought, but once you go for selling, they do not buy anything more than, they don't pay you for 24K, instead they pay you for 22K, along with minusing, right, subtracting what you can say machining charges, right? Which is also a useless technique that they use for looting people, because if you don't know how this gold thing works, then eventually they're going to just simply rob you of your honest money, right? It is very unfortunate to see that gold market in Pakistan is very, very, very unhonest compared to Arab countries. I've seen gold miners in Arab; they are very honest. They simply tell you that they're selling you 22 carat. They never say that they're selling you 24 carat, because it is by rule and by nature that 24 carat cannot be used. It is too soft to be used, to be drawn into any article like a chain or a bangle or any necklace or anything, right? Any ornamental articles you cannot make with 24K, because it would bend, it would be damaged, the shape would be deformed very quickly, compared to 22 carat, which has palladium and titanium in it, which makes it very strong and very hard, and it can retain its shape, right? Those are 22 carat. So the highest jewelry that you will find would be of 22K and below. It cannot be of 24K. This is only found as biscuits or discs, right? We call those as gold biscuits, right? These are only for monetary resourcing, not used for any ornamental purposes, right? Now there are several ways you can check silver from steel, or stainless steel. Is first thing that you check if there's a stamp number underneath it, right? You can do the same for gold. And secondly, bring a magnet. If it is attracted to the magnet, then it is steel, because silver is not attracted to magnet, right? Third, you can drop and try and listen to the sound. Remember, silver is going to make a very soft sound because it's soft metal, so you're going to have a very softer ring to the sound once you drop it. But if it's steel or nickel or any other heavier metal, it is going to be a very you can say a hard knocking sound, right? So if you get a hard knocking sound, then it's not silver. So this is an acoustic test. We call this as acoustic test or sound test, right? You can do this easily with the articles at home, but don't go breaking the jewelry of your mother, because I won't be held responsible. I would say this: do not try. I wouldn't say at home. At Let's call it at home with mom's jewelry, right? So don't do this. I won't be held responsible, right? So if you break any of your mom's jewelry, that's on you, not on me, right? Okay, now moving on, we have purity of water, right? So purity of water, we do know that most of the water on earth is actually sea water, right? That's 90, 90, I guess 98% total water, and rest is the fresh water that we drink and use, and the groundwater and whatnot. So majority of the water that we see is seawater. That causes the rain as well, right? Rainwater is also contributed from the seawater. Once the seawater evaporates, it causes the rain. So out of the seawater, so if we have, let's say, 90, 6.5% seawater, right? That's water, and it has 3.5% salts, right? So that's the composition, which is this one, right? This part over here. Now, if I project this part into this hole, then let's see how much of these salts are differentiated. Then each one has a different category, out of which sodium chloride is the major quantity, right? That is the major quantity. Then we have this sodium sulfate, right? And we have, calcium chloride and magnesium chloride, and finally we have this other salts, right? Other sulfates and these things. So NaCl is a major quantity in your salt, seawater salt, right? In Pakistan, we actually mine this NaCl, but India doesn't have any salt mines, so they actually draw their edible salt from seawater. So they take seawater, they dry it up, and then after drying it up, they have to remove these salts from it. Some of these are not healthy for us, so we have to remove them through different processes. That makes it very costly. In Pakistan, the salt, like one salt bag, costs about, right, 50 rupees per kgs. But keep in mind that in India, although the Indian rupee is more expensive than Pakistan rupees, it still is costing about 300 Indian rupees, right? Indian rupees for 1 kilogram. That is roughly about, you can say, 900 rupees Pakistanis, right? PKRs. We call it PKR, right? So in comparison to India, Pakistan has very low cost salt. We just pay 50 rupees. They are paying 900 rupees for the same bag of salt. Reason being, they don't have salt mines, pure salt mines of, we have Kira mine uh, in Pakistan that is giving you pure NaCl. It's a beautiful gift from Almighty for us, for our nation, that we are having nearly infinite amount of salt coming in, and we don't have to pay for it. Eventually, I mean, if we go to any restaurant, we don't pay for salt independently. But in Indian restaurants, if you ask for a little salt jar, I mean, for sprinkling salt on your egg, let's say, you know they'll charge you for that. They charge 10 rupees for it, right? Indian rupees. Keep in mind, Indian rupees are more, right? So they charge you 10 Indian rupees if you want to pour a little bit of salt on your egg. Usually they are not very abundant with the salt, and they charge you for even small amounts of salt that you're using in the restaurants. While in Pakistan, I think we waste a lot more salt than these Indians would be doing so, right? So again, for this, we also have percentage calculations. I would rather advise you to go through this percentage purity, right? Purity calculations, percentage purity of NaCl, right? Let's say if you had 100,000 gram of seawater. I'm writing seat water. Let's call it seawater, right? If you got 1,000 grams of seawater, right? Out of that 1,000 gram, we do know only 3.5% is salts, right? So that makes it that only 3.5% is the salt, right? So we can surely say that this is 3.5% into, you can say, and 100, sorry, 1,000 grams divided by 100%, right? This is the percentage purity that we use for mass calculation. So mass of salt would be this, right? So this would be like 35 grams only, right? So out of 1,000 grams of seawater, only 35 grams is sea salt. We call it sea salt. And out of that, I think we have about 68% NaCl, which is like edible salt, right? I'm going to write edible salt, right? Only 68% is the edible salt. So let's do the calculation again. So we have 68% in 35 grams, So we're going to divide by 100% again. So it's a double calculation for percentage. So mass of NaCl now. That was mass of sea salt, right? That was the whole salt, which has other salts in it. Now we're just trying to calculate the edible salt, because this is the calculation that Indians do. We don't have to do this calculation, unfortunately, in Pakistan, because we've got plenty of sodium chloride for us. But Indians, they have to do this calculation to identify how much sea salt they're going to get after a certain amount of water that they're going to dry up, which is again a very expensive process, right? So if we do this calculation, then let me just get my calculator again, right? So it is going to be 68 multiplied by 35, right? Divided by 100. Uh, so that is going to be just 23.8 grams. So out of 1,000 grams of seawater, like 1 liter seawater, they are barely getting 23 grams of NaCl. So imagine the cost, right? Because this drying process and also removing the other salts out of this combination of sea salt is also a very expensive process. They have to use different techniques to remove those salts to get this pure NaCl. Usually they have two variants, and in Pakistan we only have pure salt, right? Because we mine that, we have purest NaCl mine, but they have impure salt as well, which is low cost. Maybe it's about 600 rupees, Indian rupees per kilogram in India, right? Indian rupees, I'll call it INR, right? Uh, and the pure one, I mean the one we have in Pakistan, commonly available, right? We don't have the impure version. We only have the purest one, because we have the gift from God. So they are paying about 900 Indian rupees per kg, right, for a pure one, right? The one we use in our daily life. It's very costless in Pakistan. For 1 kilogram over there, it's too expensive, right? So that's how it is. I just want to say that if you've got any queries regarding these calculations, let me know. We can cover these up in the classroom again, right? Moving on to the third topic, which is the climate change. I was talking about this today in class, that I'll be using this instead of the book content. Reason being that what is weather, right? Weather. I'm just going to make it a very simple summary, that it is a short-term state, right? It is the short-term state of atmosphere. And what is the atmosphere? Atmosphere is this outside layer, right? How the outer layer, this gases, whatnot, humidity and all that. I was telling you about that. You can read that. You must read that from the book once, right? But for understanding, this lesson is going to help you understand better, because it's got better imagery than the book, right? So it's a short-term changes. So it gets rainy at times, then it gets sunny. So those are called weather changes, and can change within minutes or hours, right? That is what we call as weather. And the study of weather is called meteorology, right? So you do know there's a meteorology department in Pakistan that is giving you all these information, that when it is going to be raining, or when it is going to have a sunny, or when it's going to be an arid environment, right? Compared to that, when we talk about climate, right? It is a long-term pattern of weather, right? How a specific region is going through long-term changes. So average weather over many years in one specific place is what we call as climate, and this is what we call as climatology. Reason being why these two subjects are different. Reason being they have different instruments to work with. These are short-term instruments that we use in meteorology. We have techniques that are dependent upon minutes and hours. They're taking readings on and smaller fragments of time, while the instruments that we use in climatology and the science, or the scientific relationships that we use in climatology, are very long-term changes. So the temperature changes for, let's say, Pakistan over the years, how global warming is affecting, that would be climate. But we would not consider global warming when we're talking about drastic changes over the week, or over the days, or over the minute or hours, right? For short term we call it weather, for long term we call it climate, right? Now let's get to climate zones, right? What are climate zones? These are permanent zones. As I said, these are permanent long-term weather effects, right? So there are few climate zones which are there. Although the tundra is not there, I will mark the tundra with the orange, right? Let me just put it there with the orange. tundra, and tundra are like snowscapes. So tundra is somewhere around here, right? This is the Arctic tundra, right? This is the zone. Oh, it's giving. Sorry, it's giving a bad color. Let me just remove this. Let's see if I can get uh, some different color. Okay. Oh, it's also matchy. Let me choose a different color though. Give me a moment. I need to. Let's take pink, right? Let's call this as tundra as pink, right? And hope let's this color works. Oh, it's too big. Okay. Yeah. So this is the the tundra range, right? This is the tundra region where you see very cold places. I mean, some of this is also tundra. So this is how the tundra ranges work. There are 7 ranges in your book. Please consult the map available, this chart available in your book. Why these zones exist, I'll tell you in a moment. But first, let me explain what this is. This is the North Pole and this is the South Pole. You do know that if you look at the sunlight, then the equator is closest to the sun, right? If this is the sunlight, then obviously the polar regions are farthest away because Earth is very big. So definitely it does account for the distance. So the farther we are, the colder those zones are, and the closer we are to the sun, the more temperate or the more hot those zones are, right? So in the middle we've got the tropical zones, right, where the temperature is very hot. Then we have the subtropical or the temperate zones, right, which receive average heat and average cold. And then we have the polar zones, which receive the most cold and barely get any sun, right? So these are the maps. As you can see, if you unwrap this ball into a flatter region, this is how the map is going to look like. Now over here, one thing is very odd, which is the mountain, right? Mountains are the exceptions over here, right? One mountain range is here, which is the Himalayas, and this is the another mountain range, which is the Mexican side, right? Then we have in the American side, the Canadian side, and then we have some in Europe and some in in the Asia. So in this is also Asian part, which is the Himalayas. So these mountains, why they are separated? Because mountains count as tundras or taigas, which are like very cold. Reason being due to their altitude, they appear to be above the atmosphere and a general atmosphere which is hotter, so they don't get much of the hotter environment and hence they remain cold, being very high. Other than that, these regions are are marked that the arid is, these are the yellow ones are the arid, the green ones are the temperate ones, these blue ones are the polar ones, this pink ones that I marked, these are the tundras. These are also snowlands, right? Then we have the mountain ranges, which are these dark blue, and Mediterraneans are these few orange parts, right? These some of this Europe and whatnot. And then we have the tropical region, which is the Africa, this Mexico and some of the Australia and Asia. These are the tropical regions, right? So let's talk about the conditions. In the polar region, it is very cold and it is dry all the time compared to the tundras, which are cold but may not be dry because mountains they do have some rain and snowfalls going on. But on polar region, you barely get to see any snowfall. Reason being, it's so dry that everything is condensed into ice, so there is barely any rain or any snowfall. So it remains dry. While on mountains, we do see during summers they get some rainfalls or snowfalls. Example would be Himalayan range. For polar, it would be the Arctic or Serbia. I needed to write Serbia. Sorry, there's a mistake, right? Serbia, Greenland, these are like polar regions. Then we have the temperate regions, which are cold in winter and mild hot in summers, right? They get mild summers like North America. Then we have Mediterranean, which got mild winters and hot and dry summers like California, which is a very dry hot weather, but it barely gets any winter. Then we have the arid, which are hot all year long. They barely get much of the winters. If any of you has been to Arab countries, they would find in or even Africa, you'd find that even in winters the temperature barely gets to 16 degrees, not more. Unlike us, which are in the Mediterranean, or you can say in the temperate region. Pakistan is more of a temperate, so we have more versatility of the fruit and whatnot. And then we have the tropical, which are hot and wet all year long. And why they're wet? Reason being, it is so hot that water keeps on evaporating, and that evaporation keeps on causing more rainfalls. Hence, the Central Australia, it's very tropical region, and these are green zones we call as like the plantation zones. A lot of rainforest and whatnot are found on these regions, right? Now, moving on, we have the climate and the ice ages. I talked about this in the classroom that for ice ages, I will not be using much of these. Reason being, I'm not able to find better maps which are available in your book compared to those available on the internet are more scientific in nature, right? I haven't been able to find any more that is suited to your age, but I'll just go through a basic idea that there are ice ages ever since Earth has been there. There has been ice ages and hot weathers and hot and cold sessions. Currently, we were done with our ice age. Now we're moving into the hot, and as you can see, the global warming is going, so the temperature is going up. So there is going to be less ice. Ice is going to melt down, and it's going to be a big meltdown in future. So that is going to be the end of the opposite of the ice age, what we call as interglacial region, right? We do have presentations coming on Thursday by three candidates regarding these, so I'm not going to go into detail of this because I would rather want those students to explain this to the class, right? Now, moving on, atmosphere, right? What is atmosphere? It is the upper part of the all the gases, everything that is above the surface of the earth, that forms this gaseous coating or sheet on the above the surface of earth. We call this as atmosphere, right? And what it does and how it affects the climate is that once the sunlight comes in, the atmosphere allows some of these radiations to come in. But unfortunately, due to the greenhouse gases like the carbon dioxide, like carbon emissions, right, they entrap some of this heat, which is causing global warming, right? Usually when the sunlight comes in, the radiation comes in during the day. At night, that radiation is emitted back out into the space, right? So that is why night is supposed to be cold. But as you see, with the global warming at increasing rate of the global warming, we see that nights are getting hotter. Reason being, at night, the radiation which is supposed to leave off the surface of earth, right, which is supposed to be emitted back into dark space, is not getting back. Reason being, the greenhouse gases keep on reflecting them back onto the surface, right? And that overall is affecting the general temperature, average temperature of the surface of earth, right? This is what we call as global warming, right? So what really happens, that solar radiation passes through the clear atmosphere during the day. Part of the solar radiation is reflected by Earth's surface and by the atmosphere, right? Some of it is reflected back. Now, part of the infrared radiation passes through the atmosphere, but most of it is absorbed and re-emitted in all directions by greenhouse gas molecules, right? The result of this is warming of the Earth's surface and the lowering of the atmosphere, right? Because of this, the atmosphere becomes lower, right? It becomes very condensed because the temperatures are getting higher, and it becomes very thin. The spreading is more because when we do know when things are heated up, they expand. We do know the balloon experiment. If you fill a balloon and then heat the balloon up a little bit, you see that the balloon would expand. The same thing is happening, that the atmosphere is now getting thinner due to this global warming, so less oxygen availability would be there in percentage, right? And also the temperature of the surface will keep on increasing, right? Now there are other topics in this, which we have renewable energy, and we have bioplastics and whatnot. I will do cover those tomorrow in the class, right? So if you've got any queries regarding these topics, so please make a note of these. We'll be covering those in this week, and on Friday or maybe next Monday we will have our assessment of this unit, right? I hope I was able to clarify most of these concepts, and please go do understand this. Structure of atom is really important for your future studies, because in the next classes we will be extensively using this atomic model, and we will be deciphering the properties of different materials. I was telling over here that metals, plastic, glasses, organics, why they're different because of their structure of these atoms, how these electrons and protons are arranged. That defines how the properties of the material is changing, right? Thank you for watching this. If you've got any queries, please you may post a comment or you may ask in the class. Thank you so much. Bye bye.